everybody, getting ready to do lesson 4.5 part 1 classwork today, pre-calculus math. Today 4.5 part 1, graphs of sine and cosine functions. We have 56 points here on your classwork. 0 points of notebook taking, hooray! And today's bell work teachers for your students. Convert the angle measure, 107, 108, convert the angle measure from radians to degrees. So radians to degrees. Give your students 5 minutes. Okay, welcome back for today's bell work. Our solutions today, students, 8.5 radians equals 487.014 degrees. Here's your conversion factor here for radians, and then negative 0.48. When you convert that to degrees, here's your conversion factor here, 180 over pi. You get negative 27.502 degrees. Students, you should have that. Okay, today's page 1 classwork. Basic sine and cosine curves. In this section, you will study techniques for sketching the graphs of the sine and cosine functions here. So the graph of the sine function is a sine curve. Here is y equals sine x here, and this is how it kind of goes through the origin. You have a period of 2 pi, and you have a range here, amplitude of 1, negative 1 and 1. And then the black portion of the graph, this portion here, represents one period of the function and is called one cycle. So from here to here, where you have one max, one min, and then back to the x-axis, that's called a cycle. And then one cycle of the sine curve. The gray portion of the graph indicates that the basic sine wave repeats. So this just keeps going like that. Page 2. Indefinitely to the right and left, so this just continues indefinitely. The graph of the cosine function is shown. This is your cosine. Your y-intercept is up here at whatever the amplitude is. In this case, it would be 1 here. And then this is your min here, would be negative 1. Your period is 2 pi. To produce these graphs with a graphing calculator, make sure you set the graphing utility to radian mode. So to graph these, your graphing calculator has to be in radian mode. The domain of the sine and cosine functions is the set of all real numbers. Moreover, the range of each function is the interval, negative 1 and 1, and each function has a period of 2 pi. So here's your period here. And then your, they call it the range here, or the amplitude. They haven't called it amplitude yet, but it is the amplitude would be 1 and negative 1. To sketch graphs of basic sine and cosine functions by hand, it helps to note 5 key points of one period of each graph, the intercepts, the maximum points, and the minimum points. The table below lists the 5 key points on the graphs of y equals sine x and y equals cosine x. So here are your 5 key points for sine x and y equals cosine x here. So that would be how it alternates here like that. Notice that. So pi over 2, etc. The sine curve is symmetric with respect to the origin, whereas the cosine curve is symmetric with respect to the y-axis. So these properties of symmetry follow from the fact that the sine function is odd. The sine function is odd, whereas the cosine function is even. So the sine function is symmetric to the origin. So sine, that makes it odd, whereas the cosine function is even. It's symmetric to the y-axis here. And then here is an example here. Here's the stats on a on the f of x equals sine x here. Here's your domain. So it goes infinitely that way, infinitely that way. Your range is -1 and then 1. Your period is 2 pi here. That's your period of y equals sine x. X-intercepts is n pi and 0, and then the y-intercept is 0, 0. It's right here for a sine function. It is odd in the origin. It's odd and it's symmetric to the origin. And then for the cosine function, again, here are the stats here. Same thing, negative infinity, positive infinity, same range, same period, x-intercepts, or pi over 2 plus n pi and 0. Y-intercept is 0, 1. This is your y-intercept up here. And it's an even function. It's not an odd function. The even function with symmetry to the y-axis. Okay, so let's try an example here. Library of parent functions, y equals sine x. Sketch the graph of g of x equals 2 sine x by hand on the interval of negative pi and then 4 pi. So negative pi and then 4 pi will be over here somewhere. So note that g of x equals 2 sine x equals 2 sine x in a case that the y values of the key points will have twice the magnitude of those on the graph of y equals sine x. So this 2 here will change that. Divide the period 2 pi into 4 equal parts to get the key points. So your key points for y or g of x equals 2 sine x. 0, 0. Pi over 2 would be 2, so you have an amplitude here of 2. Your intercept would be pi 0, and then your minimum would be 3 pi over 2, negative 2. So wait a minute, pi over 2, so 3 pi over 2 would be here, and then you're down here in negative 2, and then 2 pi is 0. You're back to 0 here then on that. So by connecting these points with a smooth curve and extending the curve in both directions over the interval of negative pi is here, and then 4 pi, which on the original grid is off of it, but you get the general idea here of this function, graph of that function. Be sure to set the graphing calculator to radian mode, and then this is what it looks like here. And then this is your y equals sine x curve here. Okay, let's try an example here. I'm going to sketch the graph of this. Y equals 3 sine x. Use a graphing calculator to verify your sketch. So to do this, your period here is still 2 pi. And then your amplitude is 3 because of this number here. And then here are your key points here, 0, 0, because it is a sine function. Then pi over 2, 3. Then back down to pi when x equals pi, y equals 0. 3 pi over 2 is negative 3, and then 2 pi is 0. So this will be your sketch here of that function onto your grid, students. This is your guided practice and independent practice for the first example. Page 8 of your classwork, amplitude and period of sine and cosine curves. In the rest of this section, you will study the graphic effect of each of the constants a, b, and c, and d in equations of this form here. So y equals d plus a sine quantity bx minus c, and y equals d plus a cosine bx minus c. So this is sine, this would be cosine. The constant factor a in y equals a sine x acts as a scaling factor. So this would be a scaling factor, meaning a vertical stretch or vertical shrink. So this determines your vertical stretch and vertical, meaning your up and down. That's your vertical. So that will determine that. When a is greater than 1, the basic sine curve is stretched. So it kind of like stretches out your curves when a is 1. And when a is less than 1, the basic sine curve is shrunk. The result is that the graph of y equals a sine x ranges between negative a and a instead of between negative 1 and 1. The absolute value of a is the amplitude. There's your term there, amplitude, classwork page 9, of the function y equals a sine x. The range of the function y equals a sine x for a greater than 0 is negative a is less than or equal to y, and y is less than or equal to a. So definition, time to get into a definition of amplitude of sine cosine curves. The amplitude of y equals a sine x and y equals a cosine x represents half the distance between the max and the min values of the function and is given by amplitude equals absolute value. So knowing that, let's go right into an example here, example 2. Scaling, vertical shrinking, and stretching on the same set of coordinate axes. Sketch the graph of each function by hand. So y equals 1/2 cosine x. Because the amplitude of y equals 1/2 cosine x is 1/2, here's your amplitude here. The maximum value is 1/2 and the minimum value is negative 1/2. Divide one cycle of between 0 and 2 pi into 4 equal parts to get your key points. So maximum intercept, minimum intercept, and then back to your maximum again. So that would be one cycle. You start with max and you end with max. So you go from 0, 1/2, pi over 2, 0, pi negative 1/2, 3 pi over 2, 0, and 2 pi is 1/2, back to 1/2 again. So this would be your plots here. When x equals 0, y equals 1/2. When x equals pi over 2, it's back to 0. When x equals pi, it's negative 1/2. And then when x equals 3 pi over 2, it's back to 0. And then 2 pi would be 1/2 again. Then your plot here would be something like that. And then it continues like that. So that's a very rough sketch. So there's your sketch again of that particular function. So on the same axes, we're going to plot y equals 3 cosine x. B, a similar analysis shows that the amplitude of y equals 3 cosine x is 3. So here's your amplitude here. And the key points are max, intercept, min, intercept, max. So when we hash that out, we get something like this. This will be your plot here, because now you have an amplitude here of 3. So that is, instead of being at 1/2, it's down here at negative 3 for that one. And then for this plot here, 0, max is 0, 3. So you start up here, pi over 2 is 0. Then pi would be negative 3, and then 3 pi over 2 back to 0. And then 2 pi would be 3. So that would be one part of that function. The graphs of these two functions are shown. Notice that the graph of y equals 1/2 cosine x is a vertical shrink. So they call this a shrink here when it doesn't go as far in either direction here. It's a shrink of y equals 3 cosine x here, which is up here. So the graph of y equals 3 cosine x is a vertical stretch. So they call this a stretch. From this here, it's a stretch, a vertical stretch, not a horizontal, but a vertical stretch. Is a vertical stretch to the graph of y equals cosine x. So let's go into an example here. Sketch the graph of the function 1/4 cosine x. So to do that, the period again would be 2 pi here. So then the amplitude is 1/4. Then here are your 5 key points. We start from 0. When x equals 0, y equals 1/4. This will be your plot here when you're said and done with it. And then pi over 2 would be 0. Then when x equals pi, negative 1/4. And then back to 0 again. And then 2 pi will be 1/4 over here. So that will be your plot of this function. The graph of y equals negative of f of x is a reflection in the x-axis of the graph of y equals f of x. For instance, the graph of y equals negative 3 cosine x is a reflection of the graph of y equals 3 cosine x. So here is your y equals 3 cosine x here in the dark. And then y equals negative 3 cosine x is a reflection of that. So it's reflected through the x-axis here. You just like flip this over and you get a reflection of it. When you put this negative out in front like that, is a reflection in the x-axis. So that's what that would look like. Consider the effect of the positive real number b on the graphs of y equals a sine bx and y equals a cosine bx. Because y equals a sine x completes one cycle from x equals 0 to x equals 2 pi, it follows that y equals a sine bx completes one cycle from x equals 0 to x equals 2 pi b. It's like, wow. So go ahead and put that in your classwork. These notes are very valuable. Period of sine and cosine functions. Let b be a positive real number. The period of y equals a sine bx and y equals a cosine bx is given by period equals 2 pi over b. So our b here is going to determine our period. Note that when 0 is less than b, b is less than 1, the period of y equals a sine bx is greater than 2 pi and represents a horizontal stretching of the graph of y equals a sine x. Similarly, when b is greater than 1, the period of y equals a sine bx is less than 2 pi and represents a horizontal shrinking of the graph of y equals a sine x. When b is negative, the identity sign of negative x equals the negative of sine x. And cosine of negative x equals just cosine x are used to rewrite the function. So keeping that in mind, take this down on your classwork sheets. Let's try another example here. Scaling, horizontal stretching, sketch the graph of y equals sine x over 2 by hand. So the amplitude here is 1, it's out here, it's given, kind of like implied. Moreover, because b equals 1/2, the period is 2 pi over b, which equals 2 pi over 1/2, which equals 4 pi. So we have a period here of larger than 2 pi. Substitute for b. So now divide the period interval 0, 4 pi into 4 equal parts using the values pi, 2 pi, pi, 2 pi, and 3 pi to obtain the key points of your graph. So we have pi, 2 pi, and 3 pi to obtain key points. So we go back here to our 5 key points. We have 0, 0. We have pi and 1. Intercept 2 pi, 0. And then 3 pi, negative 1. And then 4 pi and 0. So for these points here, you're going to have something that looks like this here. So 3 pi negative 1 is down here. And then 4 pi 0, I just stretched it out over here. It's basically an extension of your axes here. And then this is what it would actually look like here for this function here. This is y equals sine x. This is y equals sine x over 2. So it kind of stretches it out. It's called a horizontal stretch over y equals sine x. Let's go into an example here, okay? We're going to sketch the graph of this function here, and then we got this one down here. Okay, let's try the first one up here. Our period would be 4 pi, and then our amplitude will be 1. You got a 1 out here, and then your key points are here. Here are your 5 key points for this function here, and then this would be the graph of that. And then down here, again, you have period of 2 pi over 4. So 2 pi over 4 would be pi over 2. 2 pi over 4 would be pi over 2. You have an amplitude of 1, which is in front of the sign. And then here are your key points here. 0, 0, pi over 8, 1, pi over 4, 0, 3 pi over 8, negative 1, then pi over 2, 0. And then this will be your plot of this function here. And that is 4.5 part 1. Email me here for questions or materials for the course. Thank you.